Now we're going to apply some of the previous ideas from Chapter 9 in what's called Avogadro's hypothesis.
All right, so Avogadro's hypothesis says that for a given pressure and temperature, a mole of any gas occupies a set volume. So one thing you'll note, this is called a hypothesis. This is only true for ideal gases. So for ideal gases, this is 100% true, but it's close for most real gases. And so we're going to use it as if it is true. We can apply it. You get a little bit of error, but we're not going to worry too much about that. And so Avogadro's hypothesis is going to work that for any given pressure and temperature, a mole of any gas occupies a set volume. So what this says is, this means is for a given pressure and temperature, those are your kind of environmental variables. So once you have your conditions, whatever the pressure is, whatever the temperature is, once you have a mole of a gas, then that's going to occupy a set volume. When we say a mole, that'd be a number of molecules. So what that means is for temperature, for a given temperature and pressure, the volume of a gas only depends on the number of molecules in that gas sample. It doesn't matter what the type of gas is. It only matters the number of molecules in the gas. So H2 is a much smaller molecule than CO2, but if you had the same temperature, pressure, and volume, you'd have the exact same number of molecules, right? Because to get whatever volume you would want, you need a certain number of molecules. That's going to be the determining factor. So if we want to see this in action, basically for a given pressure and temperature, a mole occupies a set volume. So what does that look like? Well, this is all still based on the ideal gas law. We're going to look at a couple of different applications, ideal gas law, Avogadro's hypothesis being one of them. So we start from the ideal gas law, and we can rearrange it to get this V divided by N, or V per N, volume per mole. So this is going to be our molar volume is what this is called. So V divided by N is the molar volume, and the volume of 1 mole of gas is only dependent on the physical properties of that gas. It does not depend what type of gas you have, right? R is just a constant. T and P are environmental variables, right? What are the conditions that that gas is under? It doesn't depend if it's nitrogen, carbon dioxide, carbon monoxide, whatever it is, you're always going to get, for that given temperature and pressure, the same volume per mole. So say we specify conditions. For example, STP, that's our standard temperature and pressure. That'd be 0 degrees Celsius, 273 Kelvin, and 1 atmosphere. We plug in those conditions, and we find that the molar volume is 22.4 liters per mole. So this molar volume relates the volume of gas to the number of moles of that gas that we potentially have. And so in this case, we can now see this relationship. Again, this is independent of any type of gas that we're using, but this right here allows us to relate liters to moles. So we can see this as kind of a conversion factor in the same way we had, say, molar mass that let us go between mass and volume for solids. Now we have a molar volume that will let us go between moles of gas and volume of gas. And one of the important things here is, again, that it doesn't matter what kind of gas we have. These gases, say helium, neon, or nitrogen, ammonia, methane, different gases, they have different mass, right? They have a different density. There's different masses in that volume. But importantly, the number of molecules is all that affects the volume of the gas. And so one of the things that means is if you need to use a gas for some, say, given situation, you choose whatever the cheapest gas that's available for, as long as you don't care about the chemistry, which, air is a pretty good choice. Generally a cheap choice. So let's use Avogadro's hypothesis. At STP, how much volume does 1.4 moles of SF6 gas occupy? Okay, so we can see that we're after a volume, right? How much volume are we after? So the volume of SF6 is going to be what we're after. And when we see in terms of what information is given, we're told we have 1.4 moles. There's not really much else going on. We do know it's a gas, so that's important. And we are given conditions. We're told we're under STP. But we don't have a lot of information as far as, say, using, like, say, the ideal gas law or any sort of processes like that. But that standard temperature and pressure does give us some valuable information about what's going on here. And specifically, It gives us the relationship of volume and moles. That's our molar volume. Once you define what the conditions of the gas are, then you know that in this case, it's going to be the 22.4 liters per mole. Get that 4 done. So that 22.4 is the Avogadro's hypothesis. It does depend on the gas being ideal, but we're just going to assume it is. Whenever you are given a gas, just assume it's ideal. There's no reason not to assume that it's ideal. So 1 mole of gas is 22.4 liters. That's only at STP, it should be noted, but if there's ever, we'll see, you'll do a participation problem, that if you change the conditions, you just change the molar volume and you can use that molar volume under those conditions. Okay, so if we want how much volume does 1.4 moles occupy, the 22.4, we know it's 22, whoopsies. We know it's 22.4 liters per mole, right? And so that's a compound unit. We know that per mole gives us that 1 mole when we're using that that conversion factor in an actual problem. So just like we've seen when you do like grams per mole, that's 1 mole that's on that side of the equation. And so we get this nice relationship with what we're looking at, the 31. So we end up, if we multiply it all out, we'd expect that our moles cancel out, which is good. And we get the 31 liters as being the volume of the 1.4 moles of SF6, based on the fact that each mole is 22.4 liters. Okay, so we can look at other gases. At STP, how much volume does 1.4 moles of N2 occupy? Or at STP, how much volume does 1.4 moles of helium occupy? The answers to all of these questions is 31 liters, using Avogadro's hypothesis when we assume they're ideal. Because all that matters for the volume of a gas at the same conditions is the number of moles. If these are all the same number of moles, then they're going to be the same volume. These are different masses of gas. N2, helium, and tungsten hexafluoride all have different masses, right? Because they have different molar masses, right? And if it's 1.4 moles, then there's a different amount there. But importantly, all of these samples have the same number of molecules, or atoms in the case of helium. It's the same number of little objects bouncing around in the gas. And that is what matters. All that matters is the number of molecules, not the type. It doesn't matter atoms, what they are, helium, neon, if they're atoms, molecules for bigger compounds, anything like that. The mass will be different, and say chemical properties of those gases will be different. But the volume would all be the same. Okay, no participation questions in this video. One more video left. Looking for any more on our set, or in this set of videos, due June 29th. See you in the last video.